Okay, everybody, let's recap the tide problem. So it's a tide problem. The tide problem is a really nice application of sine cosine curves, okay? So here's the problem. One day, Bill and Lana were sitting on a pier watching the tide come in. On this day, the high tide was at 1 o'clock a.m. So I put a dot at 1, and I made this axis go from 1 to 24 for a 24-hour clock. So at 1 a.m., I have a high tide of 5. And then with a low tide at 9:30 was -1. So I went to 6, 7, 8, 9, 9:30. I put a height of -1. So I only have half the curve. I need the other half. So I said, okay, well, when's the next half tide? I took my half tide. I knew the width of a high tide from 9:30 to 1 o'clock was 8.5 hours. So from here to here, high tide to low tide was 8.5 hours. So I had to then take another 8.5 hours. From my 9:30, I added another 8.5 hours, put me at 1800, which is the same thing as 6 o'clock p.m. So 12, 13, 14, 15, 16, 17, 18. So there's my next high tide, okay? Which means it's really a total of 17 hours for the tide. So I've got 17 hours for the full tide. So then I could graph it from point to point, okay? Now, equation. Well, first of all, we all agreed that it was a cosine. So we start out with cosine. And then we agreed that the amplitude was 3, okay? One way to do the amplitude is max, subtract the min, divide by 2, we get 6 over 2 is 3. So the amplitude is 3. Now the b, which is the frequency, is 2 pi. Always, always, always 2 pi, divided by the full tide. 8.5, 8.5, which is 17. So that's b. Now decimal equivalent of b is 0.37, but it's 2 pi over 17, or h of t is equal to 3 cosine of, and if I want a decimal of that, I use my calculator, 0.37. And now the rest of the equation, I know that the cosine curve has been moved over 1 because of 1 o'clock, so it has a horizontal transition, so that's my t plus 1, and then the entire curve is up 2, so the middle of the curve is right here, so plus 2, okay? So I have the equation. That's more accurate, but that one's easier to put in the calculator. So I actually did put this in the calculator to look at, okay? Because the next question says, well, what if there was a boat moored at the pier with a 2-foot keel? Okay, so that, keel's like, looks like that in a boat. It keeps the boat from tipping over when the wind blows on it, helps it going straight. But if you hit low tide, your boat gets stuck. So anyway, what we did is we graphed that line too. And then I actually put it on the calculator, but y equals, and I graphed it. And here's my tide, and here's my 2. So between here, I better get the boat out. If the boat is in the water here, it's going to be high ground, you're going to get stuck. So within those times, so I did my calculator, found out when those intersections were. One intersection was at 5.24, which is really like, and the other intersection was here at about 13.76. So converted that to time, 5:15 a.m. We better move our boat, and then we can keep our boat out until about 1:44 p.m. in the afternoon. Okay, that's all I have, and that is it.